Guys, in this video we are going to see an example of op amplifiers. In this particular problem we are going to see how to calculate all of these currents and also these voltages. Okay, and when we deal with op amplifiers we have to know two things. First, the current entering through this negative terminal and exiting through this positive terminal is always going to be zero. Okay, so that's the first thing. And the second thing is the voltage across this negative terminal is equal to voltage across the positive terminal. So these are the two things we have to know when we deal with ideal op amplifiers. Okay, and if this is zero, from this one we know that this 1 milliampere is not going to go through this one because there's no current entering or exiting this negative positive terminal. So this 1 milliampere must be going through this way. Okay, so this is 1 milliampere. So from this one we can calculate this voltage. If we calculate this voltage, that's going to be the voltage across this positive terminal because there's no current through this one. So this voltage must be equal to this one. Now let's go ahead and calculate this voltage. And we know that V is equal to IR. Here the current is 1 milliampere. So V is equal to 1 milliampere times 10k ohm. 10k ohm. Milli and K cancels each other and we are left with 10 voltage. So the voltage across this positive terminal is going to be 10 voltage. So we can say V plus is equal to 10 voltage. Therefore V minus is going to be the same. So V minus also going to be 10 voltage. Now if we know V minus is equal to 10 voltage, we can calculate this V out because we can apply Kirchhoff's current law right here at this node right here, this node. If we apply Kirchhoff's current law says that whatever the current entering should be equal to exiting, and for the negative terminal there is no current exiting or entering, so we know that this is 0 ampere. So we know that Ix must be equal to Iy. Okay, so from that one we can say Ix is equal to Iy. Now let's create the equation for Ix. Ix is going to be 9 minus 10 because we know that we have the voltage across this positive terminal is 10 voltage. Therefore voltage across this negative terminal is going to be 10 voltage. So this is 9, this is 10. So 9 minus 10 divided by the resistance in between, that's going to be equal to this current Ix. Okay, so this is going to be 9 minus 10 divided by 100, and in the other hand we have Iy, that's equal to Iy, and for Iy we have 10 voltage right here, and this is V out. At this point we have V out. So 10 minus V out divided by the resistance across this one, that's 1700. So we can say 10 minus V out divided by 1700. Okay, so these two are equal. Now we are trying to find V out. Let's go ahead and solve this one. This is going to be negative 1 over 100 and multiplied by 1700 is going to be equivalent to 10 minus V out. Therefore this is going to be negative 17 is equal to 10 minus V out. Therefore negative V out is going to be equivalent to negative 27. Therefore V out is going to be equivalent to 27 voltage. So this is our voltage for V out. So we solve for this one, and let's see whether we can find something using this one. We have V out and we know that this is connected to the ground, so this is 0, and the resistance in between is 250. We can find out this IW, right? Because IW is equal to this voltage, that is 27, minus 0 because it's connected to the ground, so 0 divided by this resistance in between, that's going to be 250, and if you divide this one you are going to get 108 milliampere. Okay, so this is IW, and also we can find this Iy because we found out this voltage, and this voltage we already know, and also we have the resistance in between, so we can calculate Iy. Iy is going to be equivalent to 10 minus, this voltage was 27, so 10 minus 27 divided by the resistance in between, that's going to be 1700. This is negative 17 divided by 1700, that's going to give us negative 10 milliampere. Okay, if Iy is negative 10, from the previous assumption we know that KCL, by applying KCL we know that Ix should be equal to Iy. So if Iy is equal to negative 10 milliampere, then Ix going to be also equal to negative 10 milliampere. Okay, so Iy is this one, Ix also this one. So we found out Iy, Ix, Iw, and we had to find out V1. Okay, if you look at this one, this one is connected nowhere, like this is an open circuit, right? So there's no current flowing through this one. This IC is going to be 0 because this is an open circuit, so there's no current flowing through this one. IC is 0. If IC is 0, then V out is going to be equivalent to V1. Okay, V1 is going to be equivalent to V out. We found out V out, that's 27 voltage. So we can say V1 also equal to 27 voltage. So we found out V1. Now we have to find I naught. So that's going to be the last thing. Let's see how we can do this. Let's look at this node right here. If you look at this node, for this node Iy is entering, all the other three currents are exiting. So from this one we can create a Kirchhoff's current law. Kirchhoff's current law says current entering should be equal to current exiting. So from this one we can say Iy is equal to I0 plus Iz plus Iw, and we know Iy is equivalent to negative 10 milliampere, and I0 is what we are trying to find. Iz is equal to 0 because there's no connection or anything else here, so this is 0, and Iw we just calculated, that is here 108 milliampere. Okay, 108 milliampere. Therefore I0 is going to be equivalent to negative 10 minus 108, and that's going to give us negative 118 milliampere, and that's going to be the I0 value. And that's how we do this kind of problems. I hope this helps. Thanks for watching.